Hey, welcome back! This is the third and last part of our series of videos on the Kalman filter and its map interpretation. Previously, we introduced the maximum likelihood and maximum a posteriori estimation methods, and here we will cast the Kalman filter problem as a map estimation problem. We consider again this linear dynamical system under the standard normality and independence assumptions. We further assume that Q, R, and P0 are symmetric positive definite matrices. Note that there is no matrix G multiplying WT in the system dynamics, and that we have required explicitly that the stochastic processes WT and VT be mutually and temporally independent and also independent of X0. The density functions of WT, VT, and X0 are as follows. We don't need to write the full density functions here. For example, for the density function of WT, it suffices to know that it is proportional to this exponential. Recall that this notation means W transpose times the inverse of Q times W, and we denote it like a norm because in fact it is a norm. Recall also that this notation means proportional to. The estimation problem is as follows. Given a sequence of measurements y0, y1 up to yn-1, we need to estimate the states x0, x1 up to xn. Next, we state 4 results as exercises that you should try to solve. So exercise 12 says, use the properties of the conditional density function to prove that this holds. We have denoted by y calligraphic subscript t the vector of all outputs from y0 to yt. This formula is a decomposition of the joint density function of all y's as a product of conditional density functions. So pause the video and try to prove this, and if you get stuck, a hint will follow in a few seconds. Exercise 13 is quite similar and states a result about the joint PDF of all states from x0 to xt uppercase for some time t uppercase. Again, pause the video for a few minutes and try to prove this. A hint will follow after a few seconds. In exercise 14, we derive the joint distribution of all states from x0 to xn and all w's from w0 to wn-1. Exercise 15 is a very important one. It gives a useful formula for the conditional density function of all states from x0 to xn given the output measurements from y0 to yn-1. It is important that you take a few minutes to try to derive this yourselves. The result of exercise 15 is very important. The conditional density function of the hidden system states, given the outputs, can be used to estimate these states from output measurements. Essentially, this is the a posteriori density function of the states from x0 to xn, having observed the system outputs from y0 to yn-1. By taking a logarithm, we obtain a sum of terms instead of a product. Note that the original conditional PDF is proportional to this expression. Therefore, when we apply the logarithm, we need to include a constant term. Next, we substitute the PDFs of x0, vt, and wt, and we end up with this quadratic expression. the map estimate of the states from x0 to xn, given the outputs from y0 to yn minus 1, is a maximizer of the a posteriori density function. So once again, the map estimate of the states from x0 to xn, given the outputs from y0 to yn minus 1, is a maximizer of the a posteriori density function, or what is the same, the logarithm of the a posteriori density, which we derived previously and is given by this quadratic function. We can drop these minuses and change the maximizer to a minimizer, and we end up with a minimization problem instead of a maximization problem. Now note that yt minus cxt is the output noise, Vt, and xt plus 1 minus xt is the process noise, Wt. This allows us to rewrite the minimization problem in this form. Let's see what we have here. The objective of this problem is to determine a sequence of state estimates x0 to xn that minimizes this objective function, taking into account the system dynamics and output equation. Have a look at the cost function. We're looking for an x0 which is close to its expected value x tilde naught, and a sequence of noise terms Vt and Wt which are small. Roughly speaking, we ask what the least effort that nature has put is, so we can observe these y's. Something like a mathematical statement of Occam's razor, link in the description. The weighting matrices are the inverse covariance matrices. Again, roughly speaking, a large covariance matrix leads to a small inverse covariance. Therefore, if a covariance matrix is, so to speak, large, the corresponding noise term is allowed to be large. Recall that Q, R, and P0 have been assumed to be positive definite, thus non-singular. What we have here is an optimization problem with decision variables being the sequences of states and disturbances, which can be thought of as input signals to the system, although we cannot manipulate them. This problem is parametric in the sequence of y's, and the way this works is that we give a sequence of y's, of observations or output measurements, y, and we obtain estimates of the system states and disturbances. In other words, we use the measured outputs to understand what is going on inside the system. This optimization problem is very similar to a linear quadratic optimal control problem, as we can see. We have studied these problems earlier. The key difference being that we have an arrival cost instead of a terminal cost, and the initial condition is not fixed. Here is another way to write the same problem without using Vt. Note the structure of the problem. We have the arrival cost at stage 0 and the sum of stage costs at time t, while the problem is solved subject to the system dynamics. This formulation is more similar to our familiar optimal control formulation. We can write the minimization problem concisely like this. This formulation is known as the full information estimation problem. Note that we have the arrival cost, which is denoted by Lx0, and a sum of stage costs, which are denoted by Lt of xt and Wt. Once again, this is a parametric optimization problem with parameters these y's from y0 to yn minus 1. We can then exploit this special structure to solve the problem using dynamic programming. But contrary to what we did in optimal control problems, where we started at the last stage and moved our way to the beginning, backwards, here we start at t equals 0 and move forwards. This leads to the forward dynamic programming method. We start by denoting the optimal value of this problem by v hat and star. Then we minimize first with respect to x0 and w0, and then with respect to the remaining x's and w's. See here that we minimize this expression with respect to x0 and w0, and the minimum depends parametrically on x1. So let us call this function v1 star of x1. Note that v1 star is almost the same as the map estimation problem with n equals 1. We can therefore write vn star like this. This formulation has the exact same structure as the original one, but with a different arrival cost, namely v1 star instead of lx0, and the minimization is carried out over the sequences x1 to xn and w1 to wn-1. We may proceed this way to define v2 star, v3 star, and so on up to vn star. This defines the forward dynamic programming recursion, where v0 star is equal to the arrival cost, lx0, and vt plus 1 star is obtained from vt star by solving a problem where we minimize only with respect to xt and wt. Lastly, v hat n star is obtained by minimizing vn star with respect to xn. This is the forward dynamic programming procedure. By applying this procedure, we can solve the above optimization problem, and the solution will yield the equations of the Kalman filter. But you will have to take my word for it, as we will not give a detailed derivation in this video. The map estimation approach offers a very powerful estimation framework that can be applied when we have random variables that are not normally distributed, dynamics that is not linear, so nonlinear dynamics, and constraints on the disturbances or the states of the system. Map estimation leads to the formulation of optimization problems, and these can be solved numerically. There are in fact a lot of software available online, such as Optimization Engine, for short, Open, that we have developed. So that's everything about the Kalman filter and its map interpretation. Thank you very much for watching, and goodbye.